Thank you, everyone, for taking the time to join me today to discuss blast furnace gas to boiler pressure control and how REXA can improve the performance of these valves at your plant. My name is Mark Farah. I handle metals and mining industry for REXA, and I'm pleased to have the opportunity to introduce our technology to you. For some of you attending, you may have experience with our products, so parts of this presentation will be a great refresher. For those new and looking to gain a better understanding of our technology, I'm confident you will find the webinar to be informative and gain valuable insight on REXA. So let's begin. For the webinar agenda, the topics we'll be going over will include REXA company information, a brief introduction, actuator types. To better understand the REXA technology, we need to look at other types of actuation to distinguish them from what we do. It was from the need to combine the benefits of each type of actuation technology that REXA originates and eventually took shape. A review of electrolytic technology will look at the inner workings of the REXA actuator and what makes us most unique technology on the market. The focus application will be blast furnace gas pressure control to the boiler. In order to operate efficiently and in a safe condition, it's important that the valve producing the pressure to the boiler is stable. We'll touch on many of those requirements, and then we'll touch on takeaways from the presentation and also questions. So REXA company information. The unique actuator patent and concept and company began as a small startup in the early 80s. After trial and error, the first generation model was installed in multiple industries in 2001. In 2008, the X2 generation contained key features that built upon the core technology to make it rugged and reliable. REXA's rapid and consistent growth continues with over 36,000 actuators and drive units sold worldwide. With headquarters near Boston, Massachusetts, and a service and distribution center in Houston, REXA continues to expand and grow, focusing on key industries such as metals and mining, power, and oil and gas. Let's get started by defining what an actuator is. The Emerson Control Handbook states that an actuator is a pneumatic, hydraulic, or electrically powered device that supplies force and motion to open and close a valve or damper. I will relate the functionality of an actuator to the human body. The brain communicates via nerves once the body's sensors detect environmental conditions. When the controller determines the appropriate correction signal, the actuator is the required muscles to position the valve, just like in the human body, where muscles control the movements. In terms of responding to the correction signal, controllers do not control. They make decisions and send commands to final control elements. Sensors do not control, they sense. They see, they feel, or they measure pressure or temperature in the process. Control valves do not control, they simply act as an adjustable orifice in a pipe. Actuators are the final control element that physically makes these adjustments. They are the muscles of the process plant. In the current state of actuation, actuators are soft and often get pushed around. They may be slow to respond, and their sizes can be large. Their diet for electricity can sometimes be large, and they may be continuously consuming power and air. To get comfortable and stable, they may be continuously twitching. For state-of-the-art actuation, what we are interested to achieve is stiff or rock-hard positioning. We cannot be pushed around, must be quick and accurate when the control set point changes, and be able to run efficiently with low power consumption that lives on a low-calorie diet. Finally, we have to be smart such that positioning can be configurable with diagnostics of system health. There are three types of actuator technologies: pneumatic, mechanically driven, and hydraulically driven. Each uses a different method to develop forces and create motion, all with advantages and disadvantages. First, pneumatic actuators are most common on control valves on new equipment and projects. Their advantages include low purchase price, and they have fast stroking speeds. However, there are limitations of using pneumatics. Because air is a compressible fluid medium, it needs to build up in order to create motion. This results in losses in resolution, overshoot or undershoot, and increased dead time. Even with the use of a smart positioner, the compressibility of air is an inherent problem to achieve rapid and accurate positioning. Operating costs are expensive when you include air compressor energy, dust filters, and water separators. In cold water, moisture in the air lines will freeze and make the pneumatic actuator non-functional. This graph shows the positioning performance of a Rexa actuator versus a pneumatic actuator. The changes to the black line control signal are easily followed by the Rexa in green, but with the pneumatic in red, it cannot respond fast enough and often overshoots or is unresponsive to the desired set point. With a dead band of 0.1%, which leads to a resolution of 0.1%, and a linearity capability of 0.05%, the Rexa X-Pac is the only actuator product line truly capable of matching the potential of modern control systems. Next is electromechanical actuation, most commonly found in on-off type service, which provides tighter control and frequency response than pneumatic actuators, but not hydraulics. They are good for outdoor service. However, most electromechanical actuators can have limited duty cycle, usually around 25 to 30%, limited force or torque output, and very few fail-safe options. The use of electrohydraulic actuators are common to control valves in steel plants. These systems provide high frequency response and great accuracy with the high duty cycle. They are also good for high torque applications. These benefits, though, come at a cost. High capital cost, electrical consumption, and maintenance costs add up to offset the positioning benefits. I like to use analogies. Sometimes they communicate the message, or sometimes it gets lost. The control valve is the final control element of many processes to make metal. Often the limitation of installed actuators is that they do not take advantage of today's advanced DCS systems. One analogy I like to use is the need in Formula One racing to push technology and performance between the powertrain, which includes the engine and the transmission, and the racing tire design and compound formulation. In 2005, in the F1 race in Indianapolis, some tires were failing during qualifying laps on turn 13. So the tire manufacturer suggested to have the race car slow down on that turn to keep the driver safe but reduce lap times. For valve actuator assembly controlling liquid flow, we do not need to be limited or slowed down by a pneumatic actuator. With Rexa, the pneumatic performance enables the power of the DCS to be realized. The Rexa will combine the benefits and capabilities of each of the actuator technologies into one. The simplicity of fail-last position and high duty cycle performance in pneumatics, intermittent operation of electromechanical, and positioning accuracy and fast actuation speeds of hydraulics. Okay, so let's talk about some benefits of the electrohydraulic actuator. Start with, its very unique design is like anything on the market today. The true closed-loop hydraulic system is hermetically sealed with the oil volumes approximately 95% less than those found in the standard HPU. Smaller Rexa units have as little as 500 milliliters of oil, which is about 1 can of Coke soda. There are no filters or oil changes required, making it maintenance friendly. All models can operate at 100% duty cycle if needed through the use of a brushless DC stepper or servo motor. These units are high precision and repeatable to 0.1% of span. Our modular design allows for very high thrust and torque output with high-speed fail-safe options. Operating temperatures range from -40 F to 250 F without performance degradation. Having Rexa actuators installed at major steel producers around the world, Rexa actuators are unmatched when it comes to being rugged and reliable. The actuator consists of two primary components, the mechanical subassembly and the electrical subassembly. The mechanical portion is attached to the driven device. It contains the motor, pump, flow match valve assembly, cylinder, and feedback housing. The electrical subassembly is basically the positioner for the actuator. This is where the main power supply and control signal are routed, and the origination of the 4 to 20 milliamp position feedback for connection to the DCS or other control system. Digital communications such as heart and foundation field bus are also available. We separate the electric and mechanical assemblies for ease of access and operation. There are many severe applications, for example, very close to furnaces, where onboard electronics simply would not survive. The control box can be mounted in a convenient location next to the valve or up to 700 feet away. Okay, next let's take a closer look at the REXA hydraulic circuit. This is the real area of differentiation with our technology in comparison to HPU-based electrohydraulic systems. Centerpiece of the electrohydraulic circuit is our bidirectional gear pump, which is coupled to the REXA brushless motor. The gear pump works in conjunction with the flow match valves, which are designated as FMV1 and FMV2 on the schematic. It is important to note from the size perspective, the flow match valve and the gear pump can each be held in the palm of your hand. During operation, when the actuator is at the desired position, the spring-loaded ball checks are locked in place to prevent the flow of oil through the flow match valves. The cylinder is hydraulically locked in place so the forces acting on the valve will not result in valve movement, which is observed in pneumatic actuators. But when there is a signal change, the motor activates, turning the bidirectional gear pump, which instantaneously builds pressure, allowing the ball checks to open. The oil is then transferred through the flow match valve from one side of the cylinder to the other. Once the actuator has reached its desired set point, the motor stops and the ball check are seated, stopping the flow through the system. When in standby mode, power draw to the electronics cabinet is only about 70 watts. The motors are brushless stepper or servo motor style, designed for a 100% duty cycle and capable of very high frequency response from 1 to 5 hertz. The cylinders use a dual rod rack and pinion, so the oil volume exiting one side of the cylinder is equal to the volume entering the other side. This design eliminates both the requirement for an external reservoir and the need for continuously circulating oil through the system. This also leads to another significant benefit of our technology: greatly reduced oil volumes. A small REXA system, something that would require a smaller cylinder for lower thrust output and shorter stroke length, something like a coke oven collection main, may have only about 500 milliliters of oil in the cylinder. The thin film potentiometer is directly coupled to the cylinder shaft. The cylinder type is rack and pinion gear, which delivers a constant torque throughout the movement range. The cylinder seals are rated for 2 million full strokes and 20 million dither cycles. Today's webinar will examine the boiler and turbine performance at the Jamshedpur Powerhouse number 3 and 4. Established in 1907 as India's first integrated steel plant, the Jamshedpur Works currently comprises of 9.7 metric tons per year crude steel production and a variety of finishing mills providing high-quality steel for automotive, construction, and household appliance markets. For anyone that is a firefighter or has taken a plant safety course, this symbol should be familiar. The right mix of air and fuel is the boiler's goal. Stoichiometric simply means that there's enough oxygen to mix with all the fuel so that there's complete combustion. No fuel waste or undesirable products are produced that are harmful to the environment when you have complete combustion. One thing for the utility boiler. Now, also please consider that most power plants have more than one furnace or boiler called a unit, but more on that later. What is the boiler's purpose? Such a simple purpose results in pretty amazing engineering with highly skilled folks that are, in my opinion, work like magic to run the plant safely and efficiently. We'll see that accurate and repeatable actuators is key to the boiler's success. This is a simplified diagram showing the role of the captive boilers to generate steam from combustion using blast furnace gas. Smoke oven gas is also used, but in this example contributes to less than 10% of the fuel used. Blast furnace gas challenges include high variability in gas pressure from the blast furnace. And also the calorific energy content is relatively low and can often fluctuate. What this means is that the control valve must move quickly and precisely to maintain a stable pressure set point. If these gas pressure requirements are not met, the boiler and turbine operations will be negatively impacted. The boiler will have higher blast furnace gas fuel consumption due to incomplete combustion. There will be an increase in heat loss with decreased boiler efficiency. The boiler steam pressure will not be consistent, and that will have significant steam pressure fluctuations. The temperature variation of the boiler can decrease the part lifetime. The turbine may need to operate at a lower RPM due to steam feed pressure range. Turbine operation is not optimized, and lower power generation is achieved. Let's look first at the process stability of boiler number 3 at powerhouse number 4. Over a 6-month period, the number of outliers was about 18% for the steam pressure. After additional review, it is clear that this process is not capable. Nearly 60% of the occurrences could be attributed to blast furnace gas pressure fluctuations. The blast furnace gas header pressure fluctuations from 800 to 1,000 millimeters water column. The boiler furnace burners operate effectively at 150 to 300 millimeters water column. And so what was happening at the plant during header pressure fluctuation, the operator is forced to shut off some of the burners to reduce uncontrolled combustion. This may lead to uneven heating in the boiler with steam pressure variation. The pneumatic actuator used to control the inlet pressure cannot position due to slow response and the nature of air or oxygen being compressible. The conclusion is the butterfly valve adjusting the burner inlet pressure needs a better and tighter actuator to solve this issue. So to the left is the pneumatic actuator that was having difficulty to control the gas pressure. To the right is a Rexa actuator retrofit. Notice the benefit of direct mounting to the valve without the use of linkages. Linkages can contribute to stiction and hysteresis, both of which can contribute to poor positioning. The new Rexa has a torque output of 100,000 pounds/force/inch. The valve is a 69-inch triple offset butterfly with tight shutoff. The fluctuation from set point of gas pressure pre-boiler was reduced from 45 millimeters water column to about 12 millimeters. In this chart with the pneumatic actuator before, please observe the left side of the chart. The red header pressure and blue gas burner pressure look similar, which is not what you want. It's not controlling the gas burner pressure. The pink line is the volumetric flow rate of blast furnace gases, which you want it to be stable. The gas pressure above 500 millimeters water column is above the rating of the burners. To the right of the chart, the blue boiler gas pressure improves but still has pressure variation and gas flow variation. The pneumatic actuators is not predictable. In this chart with the Rexa actuator, please observe the left side of the chart. The red header pressure is still unstable, but the blue gas burner pressure is controlled at a preferred lower pressure target near 250 millimeters water column. The pink line is the volumetric flow rate, which is stable. The right area of the chart, the blue boiler gas pressure is vastly improved. The gas pressure is stable and tightly controlled due to the hydraulic stiffness and precise positioning with the Rexa actuator. In this graph, the boiler efficiency improvement is clearly shown. The graph is tracking blast furnace gas flow and steam flow before and after the actuator upgrade. The red line is the gas flow, which is fairly similar in the range of 73 to 87,000 cubic meters per hour flow. What is significant is that the steam flow increased roughly 13%. This can be attributed to a more stable blast furnace gas boiler feed pressure, which improves the combustion efficiency and lowers unwanted emissions. This is a significant operating cost savings to the plant, more steam for the same amount of blast furnace gas. Another boiler application retrofit at the powerhouse was at number 3, boiler 7, where a 20,000 pound force inch torque Rexa rotary actuator replaced a pneumatic actuator. The fluctuation from set point of gas pressure pre-boiler was reduced from 25 to 10 millimeters water column using Rexa. The customer told us that stable steam header pressure for the turbine will lead to increased in-house power generation, a minimum of 1 megawatt, once the other 3 actuators are retrofitted to Rexa. This graph is a trend comparison of 3 boilers in incoming blast furnace gas pressure. The black line is the blast furnace gas pressure before the control valve, which is very unstable. The red line is the Rexa actuator. A closer look at the gas pressure before the boiler shows the Rexa actuator significantly more stable and precise than the other 2 pneumatic actuators using gas from the same header. So let's go through some takeaways from this. In summary, the Rexa actuators provided the following at Tata: improved boiler operation and reduced steam pressure variation to the turbine. The pressure set point was reduced and pressure range narrowed from 40 to 50 to 10 to 15 millimeters water column. Improved combustion with reduced emissions. The steam pressure fluctuation was reduced significantly on the output side of the boiler, which helped them conserve more steam in turbine operation RPM. The turbine RPM increased for a more efficient operation. Finally, a statement from the end user that basically states that Rexa improved their operations by rapidly and accurately positioning the butterfly valve. The result is in alignment with Tata's corporate objectives, such as energy efficiency and reduced emissions. I'd like to acknowledge the following individuals in India that worked with the customer to upgrade the actuators at Tata Steel: Shailesh Sharma from Credence Automation and Chintan Chotoi from Eyesight Technologies. Both of their contributions were critical to tell this success story. Thank you very much for your time.